Hi, everybody. Thank you for your patience. I'm sorry it took so long to get this rolled out, but uh, th this is the best I can do, and I hope this at least works for some of you. Um, and I've heard some of you say the Khan Academy videos were good. I'm glad you find them helpful. Just realize that, Sal Khan does things a little differently than what I would do. So this is my attempt at least doing a presentation that would be somewhat close to what I would do in class. So I'm going to pick up where we left off, which is section 3.3. This is the first derivative test. Um, so so we're going to start with just definition, what a function increasing means. And increasing means that if you have x1 less than x2, then f of x1 is less than f of x2. And all that means is that, well, when you draw a graph, oops, it's not good. So here's the x-axis, right? Here's x1, and here's x2. That if I look at f of x1, which is over here, and then f of x2 would have to be bigger than f of x1, or f of x1 has to be less than f of x2. So f of x2 could be up here. And that means that the function might look something like this, right? Which means it's going up, it's increasing, right? So at least I hope that helps explain the definition that as x gets bigger, y gets bigger, right? So what does it mean to be decreasing? Well, same picture, but just in reverse, right? So now this is my x1. Let's say this is my x2. Now f of x1 would be bigger than f of x2 down here, right? So what that means is you might have a function that starts here and then goes down like this. So that would be decreasing, right? Now keep in mind that not all functions are going to be increasing or decreasing. They can be doing both. For example, this function might take a turn and come down here, in which case, at least roughly from here to here, we could say the function is decreasing. And then from here to here, we would say the function is increasing, right? So it depends on the interval. So that's what they're talking about when they're talking about an interval, is where is the function increasing and where is it decreasing. Okay, so so this is kind of a clumsy definition of what it means to be increasing or decreasing. There's a much easier way to determine if a function is increasing or decreasing, and that's just to look at the slope of the tangent line at a given point, right? In other words, take the derivative. So if you take the derivative at, let's say at x1 here, the derivative f prime at x1 will be a number, and it'll be the slope of this tangent line here, or at least pretend it's a line. Now, what would be the slope of this line? I don't know, maybe 1/3, 1/2, something, but it's not negative, right? It's definitely positive. It's definitely greater than 0. So at least at this point, we can say that the function is increasing. And so that's this theorem here. If the derivative is positive, at least at a specific point or on a specific interval, then we can say the function is increasing on that interval. Right? On the other hand, if we pick a point, say right here, let me try again. Say right here, this would be x3. Then if we take the tangent line at that point, the derivative will be the slope of the tangent line, and that would be negative, less than 0. So if the derivative is negative on an interval, we can say that it's going to be decreasing on that interval. Make sense? There's a third possibility, of course. Will be way down here. Give me a second. So Here's a third possibility. Let's say this is my x1, way over here is my x2. Suppose that the derivative was 0, not just at these points, but everywhere in between, right? So for all these points, we get a function whose derivative is identically 0. And what that means is that it's flat. It's horizontal, right? So when f of x1 equals f of x2, we say that the function is constant, right? In other words, when the derivative is 0 everywhere, it's going to be a constant function. So here, the derivative is going to be 0 for all x between x1 and x2. So that's what we mean by a constant function. Now, be careful, because you can have a derivative equaling 0 at a specific number, say at x, right? And that happens actually here as well. In this first example, so if this is my x here, if you go straight up, okay, that's not straight. All right, let's try. See, I'm getting used to this pen. Apologies. So if we go straight down, this is my x, then at this point, the derivative will be 0, but not right before it, not right after it. Only at that one point, right? In other words, that's a critical number. X would be a critical number because the derivative is 0 there and nowhere else. On the other hand here, all these x's are critical numbers, right? So you can have a whole bunch of critical numbers where the derivative is 0 everywhere. So that's what we mean to be constant, right? So the next thing we want to do is figure out, well, where is the function increasing, where is it decreasing? And the way to do that is to essentially first find all the critical numbers, because the critical numbers are where it changes from, say, increasing to decreasing or decreasing to increasing. Try that again. So at this x2 here, that would be a critical number because the graph changes from decreasing to increasing, and in particular the slope would be 0 at x2. Right, so the derivative at x2 would be 0. Right, so our critical numbers are where the graph changes from either decreasing to increasing or increasing to decreasing. Right, and so we would look basically at a number line, mark off the critical numbers, and then notice for the derivative, right, before it, because it's going down, the derivative would be negative, and then after it, the derivative would be positive, right? And in the first graph, it's the exact opposite. If this is my critical number x, before the derivative was positive everywhere, and then afterwards it's negative. So, right, so the idea is to look at the intervals and then use your critical numbers as sort of dividing points, and then determine where it's going to be positive and where it's going to be negative. Does that sort of make sense? So once you indicate the critical numbers, then you draw the number line, mark the critical numbers. On each segment, determine whether it's positive or negative. In fact, that shouldn't be too hard to do. You look at the derivative, you plug in a number on the interval. If it's positive, great, mark it as positive, and if it's negative, mark it as negative. Right, and yeah, so if it's positive, we know it's increasing, and if we know it's negative, it's decreasing. Okay, so again, this might not make much sense at the moment. Let's actually look at an example. So give me a second. So example 1. We're going to be given a function, say f of x is equal to, let's start with x to the 5 minus 5x to the 4. That's 4. Plus 5x cubed plus 10. Okay. And the question is to find the intervals on which the function is increasing and decreasing. So find the intervals, I'll just call it I. Find I on which f is increasing And then we'll do the same thing for part B, on which f is decreasing. And, where would it be constant? Well, it's not going to be constant anywhere. This is a polynomial. You remember polynomials just go back and forth, so they wiggle like this, right? So it's not going to be constant anywhere. Or if they ask that, then the answer is nowhere. So, okay. So how do we do that, right? Well, remember, step one, we have to find the critical numbers. So how do we find the critical numbers? Remember, we take the derivative and we figure out where does it equal 0. So what's the derivative of this? Well, I hope you can do this by now, right? Just use the power rule, 5x to the 4th, right, minus 5 times 4, 20, x to the 3, and then plus 15, x to the 2, right? Plus 0, the derivative of 10 is 0, right? So that's the derivative. Where does it equal 0? Actually, before we do that, let's remember, critical number is where the derivative is either 0 or does not exist. Well, this is a polynomial. This is going to exist everywhere for all real numbers. So in this case, we only have to worry about where the derivative equals 0. So how do we solve this equation? Usual way. Let's factor out the greatest common factor. The GCF is 5x squared. So when you divide, you just get x squared minus 4x plus 3 equals 0. Right? So we can go one step further. We can factor, or you could actually use the quadratic formula to solve this, but I'm going to just factor it out, right? What two numbers multiply to 3 and add to negative 4? So negative 1 and negative 3. Right. So the 5 is just the coefficient, right? The 5 is not a critical number, right? It's x squared equals 0, giving you x equals 0. Right? You can actually divide by 5. That doesn't matter. And x minus 1 is 0 when x is 1, and x minus 3 equals 0 when x is 3. So yeah, so don't forget the x squared. That's a factor. When that equals 0, x squared equals 0, that gives you x equals 0 here. Okay, so we actually get 3 critical numbers here, right? 3 critical numbers. So that's your step 1. Step 2, well, first of all, draw a number line. So I'm going to do that. I'm going to do that here. So this is step 2. Here's my number line. And I will just mark off the 3 critical numbers. 0, 1, and 3 is over here. 2 is not a critical number, right? And we're going to draw a sign chart for the first derivative, right? So on each of these intervals, in fact, let's write down the intervals here. The intervals are from negative infinity to 0, and then from 0 to 1, and then from 1 to 3, and also from 3 to infinity. So these are the 4 intervals divided by these 3 points. Okay, and the derivative is going to be 0 at each of these critical numbers, 0, 1, and 3. Okay, so what's next? Now we have to pick a segment. Let's say when x is less than 0, we want to figure out where is the derivative, is the derivative positive or negative there? Okay, so I'm going to do that this way, over here. So pick your favorite number that's less than 0. Negative 1, right? It's certainly less than 0. Plug it into the derivative, right? Don't plug it into the original function, right? That would give you the y coordinates, right? But if you want the y coordinate, if you want to graph it, then yes, plug it into the original function. But here, remember, we're looking for increasing, decreasing. We want to know where the derivative, right, is positive or negative. So f prime. Right, so we can plug it into the derivative here, but notice the factored form might be easier, right? This is just going to be 5, which is positive, times negative 1 squared, times negative 1 minus 1, times negative 1 minus 3. And, well, let's see, this is going to be 5 times negative 2 times negative 4. So 5 times negative, right, negative 1 squared is 1. So 5 times negative 2 is negative 10. Negative 10 times negative 4 is positive 40. That's a positive number. So when x is negative, well, when x is negative 1, it's going to be negative, but I assure you it's going to be negative everywhere less than 0. If I had chosen negative 2 or negative 500, I wouldn't get the same derivative, the same number, but it would be a positive. And that's all that matters here, right? So pick your favorite number between 0 and 1. Well, it's not going to be pleasant, but 1/2. And in fact, there's an easier way to do this. But for now, if you just want to plug in 1/2, you'll see what happens here. In fact, I'll let you figure that out. Negative 1/2 squared, and then negative 1/2, or no, I'm sorry, positive 1/2. Oops. Yep, I'm picking positive 1/2. So that's a plus. Positive 1/2 minus 1, and then positive 1/2 minus 3. So remember, I really don't care what number it is. I just want to know, is it positive or is it negative? So 5 is positive, right? So that's a positive. Anything squared is positive. 1/2 minus 1 is negative 1/2. That's a negative. 1/2 minus 3 is negative 2.5. That's negative. So we have a positive times a positive times a negative times a negative. That's definitely a positive number. So that's going to be positive at 1/2. Right? But it's going to be positive everywhere in between. So these are all plus signs. And now I realize I made a mistake here. 40 is positive. This is positive. I don't know why I said negative. Oop, let me fix that. These are positive, right? Okay, good. Yeah, I don't know what I was thinking. 40 is greater than 0. These are positive. And it's going to be positive between 0 and 1 as well. All right, what about between 1 and 3? The obvious choice to pick there is 2. So when you plug in 2 into the derivative, again, it's just 5 times 2 squared times 2 minus 1 times 2 minus 3. Oops, a little sloppy there. So 5 times 4 is 20. 20 times 1 is still 20. 20 times negative 1 is negative 20. So notice that now we get a negative. So, all right, double check. This is negative here. Everywhere between 0 and everywhere between 1 and 3. It's going to be, the derivative will be negative, right? And finally, what's bigger than 3? 4. Plug that into the derivative. Again, I'm plugging it into this. So 5 times 4 squared times 4 minus 1 times 4 minus 3. Well, this is all positive, right? So positive times positive times positive times positive is greater than 0. So that'll be positive. So you notice that in some cases they switch signs from positive to negative or negative to positive, and at 0 it did not switch. It stayed from positive to positive. So what's special about x equals 0? Notice that that came from x squared here. The x squared, because it's an even exponent, the sign does not switch. The exponents for x minus 1 and x minus 3 were 1s. Those are odd numbers. When they're odd, the signs will switch. So we didn't actually have to do any of this here. We could have just used the signs, not the signs, the evenness or oddness of the exponents of the corresponding factors. But actually, you do have to plug in one number here in one of these intervals, say negative 1, because once you get the sign for one of them, all the rest follow by the multiplicities, in other words, the exponents of the corresponding factors. Okay, so I hope that helps. Now we just have to answer the question. The question was, for part A, on which interval is it increasing? And so to answer that, so step 3, part A, on which intervals is it increasing? Well, remember, increasing means that the derivative is positive, right? So where's the derivative positive? Well, everywhere from negative infinity to 0, everywhere from 0 to 1, right? And then everywhere from 3 to infinity, right? Because we're skipping over from 1 to 3, that's where it's negative. So the answer to part B, where is it decreasing, is where the derivative is negative. So that's just from 1 to 3. Oops. 1 to 3. Right? And that answers the question. Right? Now, it turns out you can actually combine these, even though we tend to exclude 0 because it's a critical number. As a practical matter, what's actually happening here is that this is increasing, and then it levels off, and then it continues to increase. So this is a critical number, even though, right, because the tangent line is horizontal here. So what I'm trying to say is that if you want to write this, for example, as negative infinity all the way to 1, and then jump over 1 to 3, and then include 3 to infinity, that's actually probably better. Yeah, we could skip over 0 because, or rather we're including 0 because the original definition means that for every, if you're going, if x is increasing, y is increasing, and that's going to be true here. Okay, so what happens at 1, again, a bad graph here, but it's going to come to this point here, and it's going to change to decreasing, and then it will continue to decrease, and then at 3, it'll change to increasing again, and so you can see that the derivatives are going to be 0 at 1 and 3, and at 0 as well, although it doesn't change sign. In other words, it doesn't change from decreasing to increasing or vice versa. All right, so that should give you an idea of how to determine which intervals are increasing and which intervals f is decreasing. So I think I'll leave it at that for now. We'll come back and do an example of using the first derivative test to determine where you have a maximum or a minimum.